2.1, linear programming, the graphical method. Example 1 says graph each system of inequalities, label the corners. So x plus y equals 5 or greater than or equal 5. How I would do that by hand is I would consider an XY table. And if I plug in 0 for x, y must be 5. So that's this point right here. If I plug in 0 for y, x would be 5. So I can see a line going right through there. All right, now. The inequality says greater than, so I know I'm going to shade up above that line. Keep in mind, I'm going to save that for later. If this was Algebra 1 class and that's all we had, we'd draw that line, we'd shade above it. Got it. But now I'm going to do the others. So x is less than or equal 7. That's going to be a vertical line. And I'm going to shade less than, so less than that. So 6, 7 right there. It's going to be a vertical line. And I'm going to shade to the left of that. Y is less than or equal 8. That's going to be a horizontal line, and I'm going to shade below it. So there's 8. Usually what you do when you graph those inequalities, you kind of hem in a region and you color it. If I color above the first line and left of the second line and below the third line, I'm looking at this triangle. That's going to be called the feasible region. Feasible region. That means feasible, believable. The points in that colored in region are possibly solutions to this system of inequalities. But what we're really going to want are the corner points of this. Okay, so there's one, and there's one, and there's one. And you really want to do a good job, because if you don't do a good job, you won't be able to see those corner points. So this one I got kind of off. I'm a little bit off, but if you're careful, you're going to see that that corner point is the point -3, 8. This corner point is the point 7, 8. And this corner point is the point 7, -2. Graph each system of inequalities, label the corners. That's what we're looking at. So then the next one, part B, I look at my x-intercept. X-intercept is when you plug in 0 for y. I plug in 0 for y, the x-intercept is going to be 8. The x-intercept, 1, 2, 3, 4, 5, 6, 7, 8. So again, think about that table. If you plug in 0 for y, you get the x-intercept. The y-intercept is when you plug in 0 for x. 2 times 4 equals 8. The y-intercept is 4. All I'm doing is kind of the same thing over here, that table. I'm plugging in 0 for y to get x. I'm plugging in 0 for x to get y. Those are my intercepts. I can see my line goes through those points. Now, since it says less than, I'm going to shade down. Down. Next one. Y is less than or equal 1/2 x. So this is the one you guys like graphing, 1/2 x. Think of it as slope-intercept form. 1/2 x plus 0. You'd start at 0 and you go up 1 over 2, up 1 over 2, up 1 over 2, that kind of thing. And then next one, y is greater than or equal 0. That is a flat line. Y equals 0 looks like this. And so if you think about it, if we're down from the first one and down from the second one and up from the third one, we're talking about inside that triangle. Now, it's not always inside the triangle, but a lot of the times there's going to be a nice shape and we'll be inside of it. Label the corner points. There's a corner there and there and there. Those are the corner points, and those are going to be really important. So this one is 0, 0. And this one is over 4 and up 2, so 4, 2. And this one is 8, 0. We're going to need those corner points for something we do later. This chapter is on optimization. Optimization, we're trying to optimize. When we optimize, we want to find the maximum or the minimum value of whatever the problem is talking about. Find the maximum or the minimum value. If an optimum value exists, it's at one of those corner points. Okay, so that's why we wanted to find the corner point. When we graph this, the feasible region just means any XY point that will work in the system of equations. Anything that will give me true statements for all three of those is feasible. But if we're finding the maximum or minimum in order to optimize, it's going to have to be at the corner point. So here's how to solve a linear programming problem. It's called the method of corners. That's the method we're using. We'll learn a different method later, but today it's the method of corners. Number one, write the objective function and all necessary constraints. That's just the problem. Write the problem. So this is your objective function, and these are your constraints. Objective function and constraints. Start with that. To graph the feasible region and identify the corner points. That's what we did. And then, actually, you know what? I just told you wrong. I haven't shown you any problems with the objective function yet. Objective function is going to be this. Here's how to solve a linear programming problem by the method of corners. I'll show you a different method next lesson or in a couple of days, but today's lesson is the method of corners. Number one, write the objective function and all necessary constraints. So what we did before were constraints. The objective function is going to be some kind of step at the beginning. Maximize z equal 3x plus 4y. That's your objective function. But all those inequalities, those are your constraints. Step two, graph the feasible region and identify the corner points. That's what we did above. Then number four, that's kind of the big important step, find the value of the objective function at each corner point. We're going to plug in a corner point into that objective function. So you'll see. For a bounded region looks like this. If you've got, your feasible region right there, that's bounded. But unbounded, sometimes it'll be like you get a line here and a line here, and you end up like this. You'd shade. I mean, I could shade out farther and farther and farther and farther and farther. There's really no way to stop the shading. It goes on forever and ever and ever. That's unbounded. Bounded is the nice ones that we like, formed like a triangle or some quadrilateral or some shape. Unbounded looks like this, all right? But either way you go, whether it's bounded or unbounded, you're still looking at the corner points of those lines that you graphed. So this one would have a corner point here and here and here, I guess. You're still looking at those corner points. But sometimes with unbounded, you might not be able to have a maximum. We'll see. Example 2, optimize using the method of corners. So first thing you need to know is we're not graphing the objective function. We're only graphing the constraints. These are your constraints. We're only graphing those. So, sometimes we can use Desmos as kind of a shortcut, I guess. So let's do that. Now, when you do this on Desmos, it just kind of randomly selects colors. And trust me on this, it's going to be a lot easier if you change them all to the same color. So it doesn't have to be red, but I like red. If you change them all to the same color, it's easier to see which region is affected by all four of these. All right. So it's going to be the darkest region. The darkest region is the region that we want. So what's going to happen is we're going to be after these corner points. And I like Desmos because you can click on it and see what those corner points are. So let's kind of sketch this. We've got 0, 2, 0, 0. All right, let's see. This one goes from 4 to 2. That's not a super important point, but that's how I would graph it. This graph is super small. So one of those goes from like 4 to 2. And there was a flat one, and there was a vertical one. And then what else? Oh, there was this one. It goes from 0 to 2. Okay, and it goes through -4 over here. So 0, 2, and here. Okay, notice I use this point up here, and I use this point here. Look at your intercepts, pay attention to your intercepts so you can help yourself draw it. So we got that. And the feasible region is right here. That just means those numbers, okay, those numbers will work for the constraints, but those numbers are not going to be the maximum. The maximum has to be at one of those corner points. So we look at those corner points. And this one was the point 0, 2, and this one was the point 0, 0, and this was the point 2, 0, and then this one was the hard one. This is why I like Desmos, because it was 0.8, 2.4. It's not impossible to figure out what that point is without Desmos. You can use algebra and use substitution or something to see where those two lines cross, but it's kind of a waste of time. It's very inefficient. I don't want to do that. So here's what we're going to do. All right, we've graphed the feasible region, we found the corner points, but what we have to do, notice we haven't done anything with this equation yet. We're going to plug all those numbers into that equation and figure out which one gives me the maximum. So for 0, 2, I would have 3 times 0 plus 4 times 2. I'm just taking this objective function and plugging in my numbers. That's going to be 0 plus 8 is 8. Okay. So I've got 8 right there. Over here, 0, 0. 3 times 0 plus 4 times 0. Well, you can see that's going to be 0. 3 times 2 plus 4 times 0. That's going to be 6 plus 0 is 6. And then 3 times 0.8 plus 4 times 2.4. It's 12. So plugging in the corner points gave me those 4 values. I want the maximum. The maximum z value is 12. And I want to pay attention to what point produced that, because that's going to be important later when we get some story problems and some actual context to this. So your answer has 2 parts. You've got that maximum value of 12, and then you've got the corner point which produced that maximum value. Part B. So again, you want to graph the constraints. I don't care to graph the objective function. We'll worry about that later. So x plus 2y is greater than or equal 10. Ah. All right. So again, I think it helps to make that the same color. All right, so check it out. If they're the same color, you can see, you would expect it to be this region right here, but that's not the region that's darkest. Okay, this is the darkest region. And, think about it. It's got to be greater than this line, and it's got to be greater than this line, so it's up here. All right, so if you're going to graph this, notice one of the lines goes here to here. Now this number is not the corner point of my feasible region, but it's just useful for me to graph it. From 10 on the y to 3 1/3 on the x. Ten on the y, whoops, 3 1/3 on the x. Ah, that's terrible. That's so hard. Okay. And the other line goes 10 on the x to 5 on the y. Okay, again, I don't really care about these points as far as being my corner points. I'm just trying to graph the line. That's a little bit better. So we want to be up above those two lines. Oh yeah, and we've got x. We got to be bigger than that one, and we've got to be bigger than that one. Okay. So above, and to the right and above puts my feasible region out here. Okay. Notice it's unbounded. It goes on forever and ever and ever. All right. So there's a corner point right there, and a corner point right there, and a corner point right there. So my graph is a little bit sloppy. You got to take your time and be really careful, or look at Desmos. Okay, so I don't want that point. I want this point is one of my corners, and this point is one of my corners, and this point. Okay, I'm looking at this region. I'm only looking at these corners. Okay, it's a mistake to look at this corner. I don't care about this point. This is not one of my corners. Or this point right here. I don't care about this. I only care about these three, the corners that define my feasible region. 0, 10, 2, 4, and 10, 0. So I've got 0, 10. I've got 2, 4. And this is 10, 0. All right. So again, after you graph it and look at the corners, now we can think about minimizing. Notice it's a minimize problem, not a maximize. But you use this objective function, 2x plus 4y. 2x plus 4y. That's going to be 4 times 10. That's 40. 2x plus 4y. Sorry, I know that's hard to see. 2 times 2 is 4, and 4 times 4 is 16. That's 20. 2x plus 4y. That's going to be 2 times 10 is 20. All right. There is no maximum on this problem. I know 40 would be the maximum of those three numbers, but because it's unbounded, you could keep making numbers bigger and bigger and bigger and bigger and bigger. So there is no maximum, but I don't have to maximize. I have to minimize. Your minimum z is 20. And there are two different points that produce that 20. You've got the point 2, 4, and the point 10, 0. Okay. Number 3, find the maximum and minimum values. So we're going to do kind of the same thing. Let's graph this thing. All right, I'm going to go to Desmos again. We've got x plus 4y is greater than or equal to 12. And x minus 2y is less than or equal 0. And y minus x is less than or equal to 6. And x is less than or equal to 6. Okay. So again, if you're looking at the same color, you look for the darkest region. It looks like it's this trapezoid-looking region right here. All right. So we need to get those lines copied over. It's kind of hard to copy some of them. You need 2 points to figure out how to draw a line. So 0, 3, and 6, 6. So one of the lines goes between 0, 3, and 6, 6. Zero, 3, and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Another line goes through the origin and 4, 2. Okay, origin and 4, 2. So origin and 1, 2, 3, 4, 1, 2. Notice those lines appear to be parallel. That's fine. Let's see. Here's a line goes from 0, 3 through 4, 2. 0, 3, and 4, 2. So let's just draw a line going like that. And the other one's vertical. X less than 6, less than or equal to 6. That's a vertical line through 6. So 1, 2, 3, 4, 5, 6, vertical line. Okay, do your best. Got a lot of extra information that's not necessary, but I'm trying to get to this for my feasible region. So color that in. That is your feasible region. Again, what that means is those numbers inside that region will all give true statements for these constraints, these inequalities. Those are not going to be the maximum and the minimum values, though. The maximum and minimum values have to be at these corners. So that's the corner point, what was that, 0, 3? And this corner point, we've got 0, 3, 4, 2, 6, 3, and 6, 6. We've got those 4 corner points. Don't look anywhere else. I don't care about this. I don't care about this. I don't care about this. I only care about the corner points that define my feasible region. 4, 2, 6, 3, 6, 6. So this one was 4, 2. This one was 6, 3. And this one was 6, 6. Okay. So we're going to plug those in to the objective function. So I have 0 plus 10 times 3, that's going to be 30. And 6 plus 10 times 6, that's going to be 66. And I've got 4 plus 10 times 2, that's going to be 24. And 6 plus 10 times 3, that's 36. All right, so you've got those values. You're looking at the maximum. Looks like the maximum value is 66. So maximum z equals 66 at the point 6, comma 6. You need both of those parts of the answers. And then the minimum value, the minimum z is 24 at the point, no wait, yeah, at the point 4, 2.